Hello, everybody. My name is Kirill Barsukov. My colleague is Sam Lightfoot. Both of us are part of the larger team at JP Morgan who work on delivering payment solutions for the bank. Today, we're going to take it back a little bit to the basics. We're going to talk about the journey that we took when we together worked on one of the large applications we deliver for the bank, and we're going to discuss tools and techniques that were used for optimizing latencies and scaling the platform. Something that we truly believe that if we are delivering a robust, well-functioning product to our clients, expecting the product to scale while maintaining the tight, predictable latencies is very important for client experience. So with that, we're going to do a little bit of introduction, so let Sam introduce himself.
Yeah, hey folks, my name's Sam. I'm with JP. Been there for nearly 8 years now, so slowly becoming part of the furniture. Over the years, I've sort of really got an interest for performance, so that's what I spend a lot of my time doing, and a lot of what we share today is what we've learned, the things that have pushed us forward. In the more recent years, I've become an open source contributor, Cassandra, Spring Data, React to Netty, and also a shameless plug here for my blog. This has probably started in the last year, which documented as well some of the interesting points of our journey and things we learned. So yeah, that's a little bit about me.
Sam has been a little bit modest. What Sam did not say is this: he's the most amazing developer I've ever met in my life, and I've been very lucky to have a fortune to work with Sam. As for me, I'm about 8 years tenure at JP Morgan. I've been working in the financial services industry for many years. I run the technology team that delivers payment solutions. And just like Sam, I'm very obsessed with latencies. Every millisecond counts, and we put very strong focus on delivering well-working, scalable applications. Can I see the show of hands just to gauge the audience? Who is actively developing? Who's the hands-on developers? Okay, decent amount.
Nice.
Okay. Product people, business owners. Okay. So we're going to keep it fairly technical. If there are questions in terms of the terms, we're happy to answer. We're going to leave some time at the end of the delivery, at the end of the session, to give you opportunity to ask questions, and we're more than happy to chat with you after the session is over. Little bit of the journey that we've taken. I know we're very big in acronyms. That's part of our corporate culture. So don't be afraid. WPI is just the name of the large platform that Sam and I was working on. RTP stands for real-time payments. Real-time payments are taking over the world. Many countries and regions provide real-time clearing capabilities when we can settle the payment from bank account to bank account within seconds without really having a fintech wallet in between. What's important for real-time payment is the latencies and performance of the platform. So those payments tend to be consumer-made payments, so it's many payments with the fairly small amounts. A lot of clearing networks regulate the maximum latencies that we, banks, can take from payment initiation to funds settling a beneficiary account. That's why latencies are very important. So when we started our journey and we deployed the MVP of our platform, it was a fairly small deployment. We was running it in a couple of data centers within the East Coast region, United States. We were running at a scale of about 50 payments per second, and our average processing latencies were like around 150 milliseconds per transaction, and 99 percentile latencies, that's what P99 is, were around 1,000 milliseconds, like 1 second. As we were scaling the platform and we're keeping focus on improving our performance, where we got, as of like a year ago, we scaled the platform to a fairly large deployment running across, I think, like 8 different geographic locations now. We run it both in on-prem data centers and AWS clusters. And we process more than 1,000 payments per second. And as you can see, our latencies came down. Average latencies around 80 milliseconds, 99 percentile latencies around 300 milliseconds. So that's kind of example of what's possible if we deploy the good old school engineering and we keep focus on squeezing every bit of performance and scalability from our solutions, our platforms. That's an example. It's actual real chart from our performance environment. 1,000 TPS, 1,000 transactions per second test that we executed, and the top line is the volume, number of transactions per second. The amber line is our latencies. So you can see that our latency variations is very, very small. So that tells you that average latencies and 99 percentile latencies are very tight with each other. And it took us many, many years to kind of get to that state. So what we're going to be talking about is how we accomplish this. A little bit of a tech stack. Nothing crazy going on. It's a Java-based microservice application deployed in the Kubernetes clusters. Spring Boot type of microservices that interact with each other via HTTP API calls. Every time we say HTTP in this presentation, it's really HTTPS. Everything is secured and everything is authenticated within our back infrastructure. We kind of almost everything Java 21, there are some packets Java 17. Still, we're using Spring Weblogs, reactive streams. Again, if you haven't played with them, do if you programming in Java. We deploy localized clusters with the global data planes, so Cassandra and Cockroach DB clusters that spread across the world. But we localize and processing within localized clusters in terms of microservice deployments. Kubernetes deployments, and as I said, microservices interacting with each other over HTTP. Fairly typical architecture. Performance work can be challenging and fun at the same time. It does require deep understanding of how the application works. Because if we think about it, when we optimize for performance and we solve issues, based on what we observe and our understanding how application works, we need to generate hypotheses about what might causing things that we see. And then we need to set up the tests, run the tests, confirm the hypothesis, and then come up with a solution. So two ingredients that become very, very important is understand your architecture, understand your application. And the second ingredient, observability. Without good observability tooling, it's very hard or almost impossible to make predictable progress and optimize the system, especially when we're talking about large-scale application. Our platform has more than 1,000 individual replica pods running in Kubernetes. It becomes kind of challenging if there is no tooling that exists that allows you to observe the big picture. While we're using the off-the-shelf commercial products like Dynatrace, Datadog, AppDynamics, we found them a little bit deficient in provide ability to observe our platform in aggregate. So while we use those tools to deep dive into details of JVM inner workings, we have our in-house build toolkit that allows us to observe big picture. Here we call it CAMS telemetry, just the name of the application that we developed and we're using. It allows us to see how large deployment behaves. It allows us to discover golden signals around API calls, API call stacks, a bit of JVM telemetry. We use native containers on the native telemetry, Cassandra and Cockroach, significant signals. Container resource usage, very, very important, since in Kubernetes, microservices run in a constrained container environment. So we had a lot of issues with microservices crashing because we over-consuming resources inside of the containers beyond the allocation limit. All right, I think Sam is going to take over.
So on the second slide, did you say I was the best developer you've ever worked with?
Absolutely.
Just get it
And
again. I did not pay him to say that, so okay, I'll take it. So by show of hands, who here has worked with or uses Apache Cassandra? For the camera, that's no people. Cool. So that gives the level. So it's a NoSQL database. It's shared nothing. It's distributed, and it linear scales. So to add more firepower, more throughput, you can simply add nodes. But really, the main thing here is this is our primary database that powers all our payments. So this today it deserves a significant piece into this presentation. We're going to be talking about it for some time. But realistically, the patterns you'll see apply to most databases, or particularly to most distributed databases. So to give some context, which Kirill touched on, our Cassandra deployment, we now run 14 different clusters in non-prod production across 4 different data centers. 3 of those in the northeast of America, 1 more recently in Singapore. So we are now a globally distributed application. More recently as well, which may surprise some people, is that we now have a deployment both on-premise in our private data centers, but also in AWS. And those replicate amongst each other. So we now have that failover capacity to go from either public cloud to private cloud or vice versa. Although there's a very much affinity from the banks still to stick to their private data centers. So they're buying in slowly, but it's a journey that they take baby steps with for good reason. So our largest cluster we've got has 72 nodes. This is our eFire cluster, which is an API called Orchestrator. This was Kirill's brainchild, and essentially now this underpins all of the payments that we process every day. So those millions we process each day, that's all instrumented, all contained by eFire. For a picture of scale, so that's over 800 CPUs in that one cluster, nearly 7 terabytes of RAM, 100 terabytes of disk. So whilst we're not Netflix, I think they've got 1,000 node clusters, which is a challenge in itself, we've certainly got some beef behind our clusters. And we replicate with RFS 3 per data center, which means for every data item we store, we have 3 copies per data center. So for any given data item, there's actually 12 copies right now. That's 3 copies in each of the 4 DCs, which gives us that resiliency profile to say, well, if things do go down in a data center, we can quickly flip over to another DC and continue processing without problem. And yeah, as Kirill touched on, really important point is that we co-locate our Cassandra clusters with our application clusters. So they essentially, their round trip times are sub 1 millisecond. If you consider 20 millisecond round trip time, 100, suddenly any performance benefits you get from your database are dwarfed by simply waiting for your packets to arrive via the round trip time. So really important point, and that's sort of illustrated in the image on the right, where you can see each Kubernetes cluster aligns directly to the Cassandra cluster in the same DC, whilst still replicating asynchronously to those other DCs. So essentially any latency penalty is all absorbed asynchronously, so the critical paths stay within a DC. So we want to talk about performance. We need to give a sort of a feel for how fast is Cassandra, what kind of writes are we dealing with, reads are we dealing with eFire. So the workload itself is very heavy write-oriented. So we've got 90% writes, 10% reads. So in our 1,000 TPS test, so 1,000 payments a second, that equated to just over 100,000 queries per second, so about 90,000 writes, 10,000 reads. But I think really if you're into performance, you're into your latencies, I think what's really impressive here as a piece of software is a P99, which is your tail latency of 5 milliseconds, with an average of P50 of around 1 millisecond. So there are very few databases that will give you that sort of performance. So having that congruent application stack that can make the most of that is very, very important. So Cassandra's quick. It's not as quick as with reads. It's part of how the storage engine's built, but it's got tails of 20 milliseconds, so it sort of inflates more than the writes do, but still very, very quick. And Cassandra, it's a Java language, so it's subject to garbage collection. This will become more apparent as Kirill dives into some of the optimizations that we looked into. So what have we got? Well, we've got fast writes, not as fast reads, but still very, very quick.
One comment I want to make before you switch to the next slide. When we were starting on our journey, we decided, let's use Cassandra. And when we're planning for our software throughput and scaling, we're like, what kind of latencies can we expect? And it's amazing that out there on the internet, the answer is always, well, it depends. So it was very hard for us to discover these specific numbers until we ran the test or until we measured things. And this is how we came up with the measurements you see on the screen.
So with this super fast speed, how can we leverage this? Well, I'd like to tell a piece of our story that isn't what you'd probably expect, and a journey that, even if you've not worked with Cassandra, maybe you've worked with another database, was sort of an eye-opener for us, and an eye-opener for things much bigger than databases themselves. And this comes down to the crux of choosing your database framework, and you could probably replace that database framework with libraries wisely. So here's a key thought. Could our database framework be hindering our throughput? Well, we were running Java applications. Anyone run a Java application, Spring Framework? Yeah, 4 or 5 people, good. Spring Framework, so you buy into the ecosystem, very, very popular. So the natural extension for us when using Cassandra was to adopt Spring Data Cassandra. Now, Spring Data Cassandra, it wraps the lowest level driver, but what it gives you is really quick development to build your queries via annotations, via repositories built in. So you can get from nothing to a POC to essentially to production ready in a very quick amount of time. And you've got Spring Data Cassandra, there's JDBC, JPA, there's a whole sort of ecosystem of those libraries. So we were running and we were doing some performance testing, which we iterate on. And what happened is we were profiling, checking the JVM telemetry that Kirill mentioned. And we were seeing very, very high CPU usage, higher than we'd expect. So we wanted to dig into this and say, OK, is it in the driver? Is it the serialization, which perhaps you'd expect? Or is this at a different layer? So we got our profiler out. Other question, has anybody worked with a profiler before, a code profiler? A couple of hands, fantastic. Very good. Got the profiler out, and in short, what they do is they tell you where CPU time and other metrics is being spent within your code base. So you can say, OK, we've got 10% in our server HTTP processing, and we've got 20% doing maybe Jackson, JSON work, for example. But what we found is that there was about 60% of our CPU time being spent in this Spring Data library, not even in the driver underneath it, but actually just Spring Data. Now, this seemed a bit, this was unexpected. You know, for sure, there's going to be a penalty to use these niceties, but 60% didn't sit right. So at this point, we did a side-by-side test. We said, OK, Spring Data, which gives us these query builders, let's measure it. What's our write throughput? And we got about 35,000 per second on one instance. We then did the same on the raw driver, so the lowest level driver that talks to the database. And that gave us nearly 4 times the throughput. And this was an eye-opener. And I think it should be for everyone in terms of the impact a library can have by the way it's coded. Now, what we did is, from here, we thought, OK, well, we've got 2 options. We can go straight to the raw driver, or perhaps we can work with Spring Data, see what they say, see what they find. So we raised an issue. We gave them our performance tests so they could run them themselves for the raw driver and for their Spring Data codes. And they came back, and it was only within the space of a week, and they said, yeah, we've found a couple of caching enhancements, I think 3 different ways to cache types that map to your query types so they can build those queries. And that overhead went from 50%, which is what they claimed, so there's a 50% overhead at that point, down to 12%. So 50 down to 12. Now, That's huge. But I think the real eye-opener is, and Spring's great, the whole ecosystem is fantastic, but this is a library being used by thousands of organizations. Thousands of people are seeing the same overhead, right? So for us, we were like, well, we didn't expect it. You almost assume when something's so well battle-tested, it wouldn't exist. Those kind of performance overheads wouldn't exist. So we went, okay, well, let's rerun our test with the optimized code. And that's what you see in the middle. So 60,000, so they nearly doubled the throughput, which is great, but it still left us with that almost double throughput for the raw driver. So where are we today? Well, we're on that raw driver. We moved all our high throughput queries to that, but it just shows you've got to measure everything, understand. We now run a hybrid, so we do use the raw, but we also use, say for tests, we use Spring Framework too.
I think what Sam is saying, if something doesn't look right, question it and find out the reasons why. Next thing that we started using at scale is a query batching. The numbers that Sam showed is executing a single statement through the driver, while the numbers are definitely impressive. The next level optimization that we put in place is to execute multiple mutations or multiple queries via a batched operation. So one word of caution is for distributed databases, there is a concept of data partitioning. So there are nodes, specific nodes on a database cluster that hold specific partitions of the data. So it's very important to, when we're considering using query batching, to make sure that the batch operations only perform operations on a single partition. Because as soon as we start mixing the operations across multiple partitions, single operation would hit essentially the whole cluster, and we're going to overload our nodes. So we came across of the post by Adam Zeppelin from Instacluster, and that kind of reaffirmed our intention to experiment with the batch queries, and we started adopting them, and we see significant performance improvement once we start deploying batched operations. Definitely, when our inputs in a platform come in as the one payment or one data point at a time fashion, there is no opportunity to batch operations. But if the data comes in a batched fashion, multiple data points, it definitely makes sense to process them via batched operations while making sure that we're hitting one partition per operation. As a matter of fact, this optimization became so impactful that we went back to our system architecture, and one of the, Sam touched on this, we have the API orchestration solution that allows us to chain the API calls based on specific execution plans that the application generates. We made the data operations batching one of the fundamental features in our orchestrator. So now, regardless of the specifics of the flow, we can instruct the orchestrator as to how to batch persistent operations while ensuring that the data partitioning is taken into the account. To enable this technique to work, you may want to consider revisiting your database model and evaluating what changes you may need to make to align the operations that the application needs to perform in a way that the data is partitioned in the cluster. Let's see what else. Compaction strategy selection is very particular to Cassandra. I think we're going to skip that slide since nobody here admitted that we're using Cassandra. Prepared statements. There are things that are kind of overhead things that happen every time we execute a database statement. And that's true for many databases, not just the Cassandra database. So once we specify the statement in a query language, whether it's SQL for relational databases or SQL for Cassandra query language or whatever your favorite database is, the query needs to be parsed through syntactic analyzer. The query execution plan or execution methodology needs to be calculated. The query needs to be compiled in a form that is acceptable by database server, transmitted to database server, then executed. While there is significant optimizations done on database servers to make those operations very efficient, it still takes some overhead. This is where the prepared statements comes in the picture, and I think this pattern is more adopted in the relational databases, but it works equally well in distributed databases as well. So in Cassandra, we can create a prepared statement, and from the time the prepared statement is created, we can reuse the prepared statement with the different parameters to execute it repetitively. So what it helps us to do is it helps us to take the hit of the overhead of query parsing and preparing the query to execution form only once. And then once the query is fully compiled and prepared for execution, every time we run that statement, we're going to transmit the query ID along with the parameters we inserted into the query. So what it allows us to do, it allows us to save CPU time on the client side. It allows us to save network bandwidth because instead of transmitting full query, transmitting only query ID and parameters. And that saves some processing logic in the database side because once the query is compiled and prepared, the driver typically identifies, at least on the Cassandra side, coordinator node that is the node containing the data. So the query execution on database cluster becomes more efficient because there is a fewer hops across the nodes containing the data to achieve the quorum. Right, and as I mentioned, Sam is amazing. So as we were switching to prepared statements, the type of prepared statements that we were running were kind of in-clause statements. We would say, do this for this set of IDs while ensuring that all of IDs sit in the same partition. That particular query pattern was not really working in a way that we did not see optimizations of the benefiting from prepared query optimizations. And Sam identified the issue, and he actually submitted the patch. And we were lucky enough to have Sam part of our team. It was pretty impressive. As I think it happened when we upgraded our system from Java 11 to Java 17. We were very excited, what's the new things come with Java 17. And we're like, oh, look, there is like new garbage collectors that are supported for Java. We're like, great. We're working on this latency optimization, and all of a sudden we see, oh, there is a ZGC that promises us maximum processors like 1 or 2 milliseconds. We're like, this is something we should definitely be using. So in the spirit of experimenting and generating the data and confirming the theories, we ran the test. We executed performance tests with the G1 that we've been using forever. And we ran the same test with the ZGC configured with our services, and that's the results we kind of got. And we looked at them, and we're like, didn't really make any difference. And that's when we said, okay, so potentially that's another pointer that tells us that our platform is really database bound, and to squeeze more performance and tighten up our latency profile, we need to double our focus on database side optimizations. So we started looking at database, and while we were on a garbage collector kind of brainwave, we're like, all right, let's see what's going on with the garbage collector impact on the Cassandra side. So Cassandra runs on JVM. It has garbage collector configured on every single node. The default distribution comes with the garbage collector configuration set to maximum pause of 300 milliseconds. Our internal install of a Cassandra that we have in-house overrides it to 200 milliseconds. Still, quite a significant time. That means you remember the statistics that Sam showed, showing that the read and write queries take 1, 2, 5, 20 milliseconds. But every time we hit a node that happens to garbage collect, we can potentially take a penalty of 200 milliseconds. Not good, right? So we started experimenting with the optimizing max pause side for our garbage collector, and we found that we're kind of in a sweet spot with the about 50 milliseconds pause. Nothing comes for free in this game. The more frequent pauses, the shorter target pause requires us to do more frequent cycles that consumes more CPU. So with the 50 milliseconds mass GC pause, we see that we're consuming about 15% more CPU, but we're significantly decreasing our maximum latency. So the graph on the right-hand side, the teal graph shows our latency profile with the 200 milliseconds pauses on the Cassandra. The amber, is it amber? Orange. The orange graph shows our latency profile for the same test executed with the 50 milliseconds GC pause. So the difference is quite drastic, but be aware of this balance of CPU usage versus how far we're compressing the latencies and how frequently we run GC cycles. And I promise you, we're not lying. So this is the screenshots from our telemetry toolkit, and you can see that with the 200 milliseconds maximum pause, we have like 230, 240 milliseconds maximum latencies altogether. And once we switch to the 50 milliseconds maximum pause, I think somewhere there we see like 60 milliseconds maximum execution time. So that allows us to get significant benefit. While While it was all good, but we still are in a situation that when we execute the query starts being processed by, in our case, 3 or 4 nodes in the Cassandra cluster because of the quorum setting. We still stand the chance that one of those nodes could be undergoing the major garbage collection and to be in that pause state where even with the reduced mass pause, we're still incurring 50 milliseconds penalty. So we started brainstorming, how do we avoid that? How can we work around those annoying 50 milliseconds added here, added there? So what we discovered, there is a capability provided by data stacks driver that allows us to do speculative query executions. What it means is we can configure a delay in a driver and execute the initial query. The driver will wait for the duration of pre-configurable delay. If no response is received on that query, the driver will dispatch same query to different coordinator node. And that allows us to alleviate the situations when our initial query got unlucky and it hit the node that undergoes the garbage collection and it's in a pause state. This query delay is a configurable parameter. We're aligning it with 99 percentile latencies. So we would wait, we'll allow driver to wait for 99 percentile latency time for the first query to complete. Only if it doesn't complete, we fire the next query, and whichever result comes back, we use the result to proceed with the execution. Once we implemented this change, on the top, you can see the graph with speculative executions disabled. On the bottom, the same workload executed in a performance environment with the speculative executions enabled. As you can see, all of those latency spikes got pretty much shaven down for the most of the time in the test.
That's amazing, right? If each of those spikes is someone waiting for their payment to process or someone to tap their card, the improvement to client experience there is unbelievable, really. Yeah. Okay.
It's you.
But we can actually take this one step further. So you might be saying, well, how do we do that with our queries? It's not built into our driver. You can actually apply the same pattern to HTTP requests. And Google did a paper on this. Jeff Dean, he said one of the best ways to curb latency variability is to issue the same request to multiple replicas. So maybe to 3 different replicas all at the same time or with delays, and then take the first one to respond. Now, obviously, there's no free lunch here. you're sending more requests, and it becomes a trade-off of your application's latency requirements versus the resources you have. But there's also one more thing that you have to implement to be able to support this, and it's a word that I really happily heard about 5 times today, and I think the talk before was on this, is that your endpoints have to be idempotent, which means that, for example, you're sending that same request 3 times to perhaps 3 different instances. They have to act as if that request only ever successfully processed once. So if you're sending a payment from me to Kirill, we don't want that to happen 3 times, or well, I certainly don't.
But I would like it.
Kirill probably does, but yeah. And then, as Kirill touched on, you can configure the delay you wait before you send that next request, that second request, that third request. And that's all depending on your requirements. The typical way to start is align it with your P99, which means that 1% of requests will be slower than that delay. So really that means is you're paying what you'll have 1% more requests in total, which is a very small cost to pay, which is what we tested out. And we implemented hedging, this technique, in 10 lines of code. So to do a POC to test it, it took a very quick time to market. But again, these were our results. So aligning with our P99 in just one service, which means that only 1% of requests would realistically hedge and send another one. We saw the dampening, so if you can just point out those blue lines at the top, the watermark. So before, at the top, I think we were at about 350 millisecond max latencies in these 1,000 TPS tests. By just hedging those 1% of requests, that max came down from 350 all the way down to 290. So in terms of bang for buck and investment capability, that was really quite amazing. And if you can see the green lines, our P99s, our P50s, they all remain the same. But what it does mean is if you hedge at a much lower fraction, at a much lower percentile, you can actually, what you will see is the dampening increase even more. So that latency profile, that watermarked line, would actually get lower and lower. So honestly, if you take away anything, if you're building web apps and you need that tail performance and you take away anything today, it should be request hedging, I promise you. And yeah, the reason it works so well is because the cloud is messy. We suffer with noisy neighbors, other tenants running on shared infrastructure who don't behave. Sometimes we don't behave because there's a bug. This is why this technique is so powerful. So Kirill touched on modern GCs. I'll breeze past this. The more recent garbage collectors in Java, they're all targeted towards doing the work in the background, so you'll stop the world pauses. Those 50 millisecond pauses are actually more like 1 to 2 milliseconds. Now, as Kirill said, we did our tests. It didn't affect our application much, but imagine if Cassandra can take that concurrent garbage collector and reduce those pauses from 50 down to 1. And that's actually what they're testing at the moment, and they're getting ready for Java 21 in order to, which will support the generational version of Z. So for us, we're sort of waiting with bated breath to be able to take advantage, but obviously we have our mechanisms to get around it. And yeah, as I said, we did our tests. Actually, our GC pauses in total reduced from 500 a minute milliseconds down to about 2 or 3. So it was great. Our CPU did go up.
Yeah, there's not a mistake. This is how low the pauses are.
Yeah, so those things work. They reduce the pauses. But there's a CPU cost for our workload. What I would say is, if you're interested, if you think this could work for you, run the tests. It's all about your workload. For us, Cassandra's GC pauses dwarf this, so we haven't implemented Z. We're not using Z, but perhaps in a couple of years or a year when they use Z, we can too.
I think we only have time for one more pattern we're going to cover, and then we're going to close it off, let you guys ask questions. So at some point, we were looking at our latency graphs around the API calls, and This is the simulated picture, but it kind of reflects the reality. We started to see the pattern where in a very repetitive periods, we see the latency spikes. And that looked very artificial. So we're like, you know what, it's not a noise in the system. We cannot blame noisy neighbors. Something that we probably are doing. Oops. So at that point, our setup in the system, we were still in HTTP1. We had a pooled management of HTTP connections. With the HTTP1, we have to use one connection for one request. There is no request pipelining where we can channel multiple requests to the same destination through one connection. Our connection max lifetime was set to 30 minutes. We're running on a native web container. And we were looking at 30 minutes here, 30 minutes, 30 minutes over there. Sounds too coincidental. We're like, well, maybe one has to do with the other. So we set up an experiment. We shrunk our connection max lifetime to 5 minutes, ran a test. Then we shrunk connection max lifetime to 2.5 minutes, run the test. And you can see the latency graphs that we got from like 5 minutes max lifetime test, 2.5 minutes max lifetime test. So that gave us the confirmation that it's something to do with the connection expiration. When we look into this further, we realize what's happening. When we bring our services up, they all kind of get deployed in a rapid succession. We initialize our connection pools that pulled HTTP connections. All the connections get associated very close to one another. So since they get born around the same time, they all get close to the die around the same time. So every 30 minutes in our system, we have the situation where connection pools get depleted because we close the connection because they get to the maximum expiration time. Now, we start reopening connection once they close, but the connection reopening is a very heavy operation, especially remembering that it's not just HTTP, it's HTTP secured over SSL. So every time we open a connection, it's a heavy cryptographic operation, requires CPU, requires multiple round trips. On top of that, we're getting hit with the peculiarities of TCP protocol. When new TCP connection is established, there is a protection built in TCP protocol that does not use full the bandwidth of the network. It gradually increases the size of the window, number of frames it sends before it receives the ACK from the destination. Because of that, the initial interactions over the newly opened channel is slower than later in the connection lifetime. So all of this resulted in a slowdown, major increase in latency, and also major spike in the CPU time. We see the snapshot of our telemetry screen that shows that the CPU spikes to like almost 3 cores, where normally it sits around like some millicores. How do we solve this problem? We modified our connection pools, and we implemented sequential connection recycling. So we essentially preventing that connection expiry storm situation, but by proactively, with some headroom before that deadline occurs, we recycle one connection at a time. And we're only closing one connection at a time, and we go to recycle next connection once first connection is successfully recycled. So that allows us to maintain almost full capacity in our connection pools while proactively recycling connection and refreshing their lifetime. To do that, we had to do some, by us I mean Sam, had to do some coding within native reactor to give us that capability. We didn't find anything out of the box, which is kind of surprising because this technique is used in database connection pools since like beginning of times, but amazingly, we found nothing for HTTP connection pools. And the result, as you can see, our latency profile became very, very flat and very predictable. So we no longer experience that connection expiration storms where every 30 minutes in our time we see connection spikes. I'm tempted to kind of say, yeah, let's close it off and see if you guys have any questions. Yes?
So you've worked through like a lot of different optimizations and different areas where you can use optimization. How do you like manage, you know, other developers creating new systems and not knowing these best practices within your company? Like, how are you kind of gatekeeping and ensuring like database connection, like all of that makes sense, or HTTP connections make sense? You know, like it's very niche knowledge about these things that most people might not have.
So the question is how others in the company learn about these niche optimization techniques and how do we ensure that they are adopted across the board? You want to take this one?
So that's a really good question. I think it's a combination of depending on the techniques we talked about. So what we use a lot of is we have like shared libraries, which a lot of those techniques go into. So if it's the connection recycling, as a platform team, everyone deploying a service with our libraries will pick that up and they'll benefit. If it's down to the hedging we talked about where you send another request, it's down to making that as easy as possible for developers to use. So for us, we have an annotation that you can put on your code to make it do that. So at that point, it just comes down to code reviews, you know, making everyone aware, sharing the knowledge. But it really is, you've got to abstract and hide as much of it away as you can because there are, as you said, you get a new developer, you cannot keep adding these things that they need to learn because it's never going to scale. So yeah, very good question.
Any other questions? Nope. Well, Sam and I were still available today, tomorrow. If any of you wants to come and chat about those topics, we're very passionate about it. Once you get us talking, we never stop. So be careful, but more than welcome to find us and ask questions. Thank you.
Thank you.